officially 1 p.m. So we will begin.
Yep.
Welcome
All right.
everybody to Nerd Academy. This is the first weekly lesson. We're going to try to do a lesson every single week for however long. We'll see how long this lasts. Today we will be discussing the usage of Desmos and motion vectors. Now, a motion vector is essentially it's like at the core of basic physics simulations, and it's going to be very crucial to use in anything related to making a video game with any kind of physics. So I will begin to share my screen so that you can see what I am doing. Okay, so we're going to begin by going over to Desmos. Now, Desmos is a very powerful graphing calculator. How many of you are familiar with Desmos already?
I use it, for example, at my math homework to check for if I calculated the asymptote of the function right.
Okay, that's
or
good.
To check if there's a function I calculated right. Yeah.
Yeah, okay, that's a good usage. Sayas, are you familiar with Desmos at all?
Not at all, no.
Okay, so basically go to desmos.com/calculator, right here.
I'm on there now.
Yeah.
I guess I need to sign up for an account.
You don't actually need to, but it's nice to in order to save graphs. So
students join your classmates. Awesome.
Yeah.
It's also available for the phone.
Yeah.
So you can insert some graphs on your phone.
Yeah, and the graphs are really cool. So the way Desmos works at its most basic level, so you got these expressions, and each expression you have, you can do a lot of things with it. For instance, you can have a basic function, like say f of x equals x squared. So this is the x-axis, the horizontal, and the y-axis is the vertical. And so what a function does is it takes a particular value of x and it feeds it into this, and that becomes the y value. So 2 squared, 2 times 2 is 4. 4 squared, 4 times 4 is 16 all the way up here. And that's basically what a function does. And they can get really complex. Like you can have, sine of x to get the sine wave and all that.
Wow.
Yeah, and all that will be explained as they come along. Now, we can also plot points. So if we plot a point at 1, 1, we can set it to be draggable. So we can kind of move it around and do whatever we want with it. If we call this point P, then we can also have P plus and say 1, 0 to draw a point 1 unit to the right. Now if we change that for a variable, like say O for offset, and replace 1 with O, then suddenly we can change this to adjust the offset. Are you following?
Yeah. Pretty
Yeah.
cool.
And so Desmos has a lot of cool features like this. Another one that would be very important is a similar function to this. See, this is what's called a parametric function, because it takes the input along the x, feeds it through the function, and then the output of that function is the y value, the elevation above the x-axis. However, we can also do a Cartesian function, which is every point in space is sampled, and it runs the function and tests for an equality or a comparison. So say we want to draw a circle using the Pythagorean theorem, x squared plus y squared equals 1. So at every position, say 2, 1, or minus 2, 1. Minus 2 squared is 4, and then 1 squared is 1. Add them together to get 5. 5 is clearly not 1, so it doesn't get drawn. However, this point right here, you got minus 1/2 and then 0.866, which I believe is half the square root of 3. If we do 3 divided by 2, yep, that's half the square root of 3. So both of those squared, minus 1/2 and half the square root of 3, produce these numbers. We got that and that. Oh, this has to be in parentheses. There. And then obviously these two added together is 1. And so that's basically using the Pythagorean theorem to draw a circle, because every single point on this perimeter of the circle, the x and the y values, square them both, add them together, you get 1. And 1 is arbitrary. We can change it to whatever we want. Now if we square it, we actually get the proper radius. So now it's actually radius 3. And if, we can change it to 4 to make it radius 4 and whatnot. And we'll use the Pythagorean theorem in more detail. For now, I'm just kind of showing off what Desmos is capable of. Now, another important feature that we will need for what we're doing are events. So if we have some variable equal to 0, we can have an event. Let's call it capital E equals V, and then the event is V plus 1. We actually don't need it to be called E quite yet. If we just hit this event thing, it just keeps adding 1 to V. We can spam click this and just keep on adding. Now if we call that E again, if we just have E, we can reference it somewhere else. Now there's also this thing called a ticker. If we run E like that, it just starts counting up like mad. So it runs this event every, well, it's not really 0 milliseconds, it's more like 10 or so. But yeah, it just keeps on counting up. And so we can use that for physics. Are you following along so far with all that information about how to use Desmos? Any questions?
Yeah.
Okay.
Yeah.
I'm going to have to check the chat regularly in case someone who's not using a microphone says something. So, any misunderstandings about how this operates, and are you kind of following along in your own Desmos graph?
So it's basically the English version of...
One at a time, please.
Sorry.
Let's see, you can, Thais, you can explain your thing first.
Sorry, I just realised that I was meant to have it open. I just had the website up. I wasn't actually in the graph itself. All right.
Yeah, you can have like Discord on one side and Desmos on the other, so you can watch what I'm doing and then do that. But yeah, the real key we're going to want to keep in mind are these events. Now, I'm going to fast forward a bit and show you what we're actually going to be making with this. So we got this little thing here. We click the circle and it applies a force to this little square. And to see how it flies through the air all nice and it bounces on the ground. Doesn't that look so nice?
Yeah.
This is what motion vectors are capable of. Basic physics simulations. And so this is what we're going to be doing. Now, the first thing to discuss is what is a vector. Now, a vector is essentially a one-dimensional array of points with at least 2 entries. That's more so the technical definition. It's in 2Ds, in two-dimensional space, you could think of it as a point or an arrow. Let's fill that in. So this could be considered a vector. More specifically, if we call this V, we could have V and 0, 0 drawn as a line. Color it green, get rid of the points. There. So this is a vector. You got your origin here at the center of the graph, and you can really plot it anywhere. And what the motion vector does is you have some position for your object. Let's start it off at 1, 1. We can color it something else. Color it black. Call it position. And this one we can call velocity. And basically what we're doing is every frame, every time it updates, it will move this far from where it currently is. Does that make sense?
Can you please explain again?
Okay, so you start with the position, and then we add the velocity to that position, which means that the next time it updates, it will move from here to this point here. So if we create an event, we can do p set to p plus v. Boom. And then if the velocity were to be moving this way, every time we update it, it moves in that direction. For it to be this way, it moves in that direction. And so the velocity vector basically says in what direction and how quickly is the position point going to move. And so if we set this up on a ticker, we can call this M for motion, and then run M, and play it. Oh boy, it goes fast. Better zoom out. Yeah, see now, wherever we put the vector, it moves. Isn't that cool? Now, do you have this created on your own graph?
Setting that up now.
Hang on a sec.
Yeah, so I'll give you some time to set all this up here. Now what I'm actually going to do, I'm going to make it a tenth as sensitive. That way I can move the velocity vector out a little bit more and you can better see what's going on. So the position point kind of chases after the purple point, which is just the location of the position plus the location of the velocity. And when you add two vectors together, really what you're doing is you're adding this x value to this x value and this y value to this y value. Does that make sense? Kind of moving a figure 8 here.
Sorry, I'm just having trouble setting that up right now.
Okay, let's see what you got.
I've been basically just trying to copy down what you've got there, and hasn't really gone well, I don't think. So, you just.
Henris, for that to get it to run, you use the ticker. So what you do is you type ticker in the expression. I already created one, so it won't do it. So you type ticker in the expression, and it will automatically create this. And then you run M every so milliseconds. So if I type M here, and click play, it starts moving. Now I can change it to go like 1000, and it only runs every second. You see how slow it's moving. If I remove a 0 from there, it'll move 10 times a second. If I remove another 0, it'll do it 100 times a second. Although I don't know when the actual cap is. If I set it to 0 and play it, oh, it looks like it is 10 milliseconds. Yeah, when it's set to 0, it goes as fast as it is capable of going. And I just usually keep it set to 0.
Okay.
I think it'd be good to get a second monitor for this so I can see Discord on one side. I only have one though. And this whole thing also feeds into calculus when we get to that point, since you might have heard the term derivative thrown around. The derivative of position is velocity. So the velocity tells you how the position is changing. That's what a derivative is. But we won't be getting deep into calculus today. For now, we're dealing with simulating basic physics.
Alright.
Pause that. And see what everyone's doing.
I've kind of got this thing set up, and second one on the thing. Yeah, I've got terrible internet. The stream's probably not going to load.
Yeah. We'll see if it loads or not.
But on the second entry, I can't get it into one of those fancy little green things you got there. I don't know how to describe it.
Yeah, let's see if
it's the icon. The icon to the left of it is a blue circle with a white circle inside of it, and I don't know how to change it into a green thing with those lines in it. I'll just send a screenshot. don't really think I'm describing this very well.
Yeah. Henris, did you hit the play button on the ticker? Because you can play and pause it on the top left. This button here. How is it acting exactly? Well, it's supposed to move in the same direction. You see, you move around the V vector, the green thing. You move around the green thing to make it move. Like this.
I just posted a picture of what I mean in the chat thing.
Okay, so Devin, to get the ticker, you literally just type ticker in the expression and it will create one automatically. There are also folders where you can call them whatever you want, like test folder, and then you can put stuff in the folder and then collapse it. There are also quotes for comments, basically, like this is a velocity vector, and then just call this velocity. Yeah.
How do you make the line again?
That's what
The
I meant
line?
as well.
Do you mean this one?
Oh, so do we like need to make the point first and then add the point and comma and another point to the origin of the graph, I suppose?
Yeah, so we have 0, 0 as the origin. We could set this to any other point and it would connect to that point instead.
Or we can like change the variable to a parenthesis or a fixed point. If that
we could move that. So if we set origin O for origin to 0, 0 and then do VO, then we can move around O and it's suddenly connecting these 2 points together. Yeah, and we could actually have more than just O as well, because if we add P and then go back to V, we got a triangle. So this expression basically tells you, like, it's a list of points, and you can draw lines between them. Since right here we got lines, we can animate the points, change the style of the line. It's all sorts of neat features. Remove those, set it back to 0, 0. And then make that invisible. Okay, the arrow. So the you basically just define a list of points like this, where you got your first point, velocity, a comma to separate it, and then your second point. And you can have any number of points that you want, and it will draw a line from point to point to point. And to actually make it into a line, you hold down the button to bring up this menu. You turn off points, and you turn on lines. You can leave points on. You could also label the points if you want to, but no real reason to. Oh, there's also this clickable event. We'll get to that soon. But yeah, you basically just turn lines on. You can change the line to whatever color you want as well. I prefer being green.
That was the issue. Right.
Yeah.
How to make that green? So you
Yeah,
click
well,
that. Yeah, you hold.
that was just answered.
Okay, yeah.
Sorry. Right, I'm just going to follow along with the rest of it now. Could you?
Okay, so I
Good
think.
thing back up, please.
Oh, how do you type the arrow? Oh yeah, the event. This thing. So what you do is hyphen, and then the this symbol here. Yeah, you do hyphen and then the is greater than symbol. The colors do not matter, they are just for aesthetic purposes. I like to, pick nice looking colors for my graphs since, it's nice to look at. So now, what's the next thing to do? Well, I suppose, now that we understand the relationship between position and velocity, now we want to understand forces and acceleration. So basically, so velocity tells you how position changes over time, right? Acceleration tells you how velocity changes
Tells
over
you
time.
what. Oh, sorry for interrupting. Can
Go on.
may I say it?
Yeah.
So acceleration changes determines the change of velocity.
Yes, exactly. And
So
I
it's the
think,
derivative of velocity.
yes. Yeah, acceleration is the derivative of velocity, and velocity is the derivative of position. And it's really fascinating. There's even a derivative of acceleration called jerk, and that has a derivative as well. I forget the name. And you can also go backwards. So velocity is the antiderivative of acceleration, and position is the antiderivative of velocity. And in calculus, you do the antiderivative by integrating with an integral, but we'll get to that later. For now, we got velocity and such. So, if we define acceleration, let's say we have an acceleration vector instead of a velocity vector. Let's make acceleration red. And we can continue to animate the velocity vector like that. We'll just kind of reorganize this and how everything's sorted. Let's have a folder for position. And then another folder for events. Just put that in there. We can remove O and replace that back with 0, 0. So now we have acceleration. We can move that somewhere. You do the same thing before with A, 0, 0. Make it red with lines so it looks nice. Okay, so now what we will do is add a second event to this. We won't just add velocity to position, but we will modify the velocity to be velocity plus acceleration divided by 10 with the scale factor of 1/10 so that it doesn't explode everywhere. And we can actually have another point right here, P plus V plus A. And you can see the relationship here. I should probably color these points better. There. And so the green point here is where the position is going to tend towards, and then the red point is where the velocity is going to tend towards. And so if I move the velocity, the red point moves with it. But if I move the acceleration, the red point, moves freely from the green one. And so if I set these to some base value and then hit play, it accelerates like mad way over there. Where'd it go? We lost our point. There it is. Here, let's slow it down a little bit. It's going all over the place. Need to get yeah, we lost it. Where'd it go? There it is. Yeah, the acceleration is kind of volatile. Whoa. As you can tell. And it's kind of hard to follow along what exactly is happening. Let's crank up the values, or the derivatives of those, not derivatives, scale factors of those, so that we can better see what's happening. So I can make it accelerate that way, and it tends towards that direction. If I make it accelerate towards that direction, the velocity chases after it. Can make it accelerate in the opposite direction, turn back around, turn that way, and so on. I think that's really neat. Now, for visual sake, I'm going to add another thing. It can be P plus V, and then P plus V plus A to draw some lines here. Let's make them black lines without points. Put it above those. And now we can see some little wireframing there. And we're forcing the acceleration to be some value, making the velocity accelerate towards that direction, and then the position is chasing it. And if you think about it, acceleration now is acting like velocity did before. Now we can still manually assign velocity and set it to wherever we want. but it will still tend in the direction of the acceleration. And so if we think of the velocity like we thought of position before, it's doing the same thing, just with another layer of abstraction. Does that make sense at all?
May you say that again, please?
Okay, so basically we have a number of layers going on here. We have the velocity layer and the acceleration layer. And like we were saying before, acceleration is to velocity as velocity is to position. And so if we ignore position for a moment, we can literally just turn the position off. Notice how the acceleration is telling the velocity where to go, in that specific direction. And so it's literally the same thing that we were doing with the position and velocity before we added acceleration to the mix. So we kind of pushed it back one layer. If we turn position back on, we can see that it's more dynamic now. And it's almost more natural in a sense, since it won't, suddenly change directions, but rather the force that is being applied to it is what is changing. I'm gonna check the Discord chat to see. Okay. Yep. Doesn't look like the Ace's stream wants to load at all. So
are you going to share with us this Desmos page at the end of the class?
Oh yeah. Yeah, and also shared this one as well. So, we're kind of going to reconstruct this one from scratch, really. So, are there any questions about how, the relationship between position, velocity, and acceleration works as has been demonstrated here?
Well, I still got stuck at replicating velocity in Desmos.
Okay, so what exactly is it doing now?
The event thing. Like, it's not... I see an error at the part where B gets assigned one unit.
If you could send a screenshot of what your current expression list looks like.
Yeah, hang on. I am seeing this error.
Okay, let's see. What does the error itself say? Oh, see, here's the problem. Is that V is a vector. It's a point in space, so it has two terms. So you can't add a number to a vector, so you have to add...
Oh, right.
Yeah.
So you gotta add, like a
like,
point,
say... Yeah, like a coordinate in parentheses. So it'd be like 1, 0.
Oh, I see.
Yeah.
But then won't it do in like one axis or something?
It'll only be on one axis, which is why we use A for acceleration. So we defined A as a point, just like we defined velocity and position as points. And so you can add one point to another point just fine.
Okay.
Just like this, or this. You just add a bunch of points together. And when you add points together, it's really like you're adding all of the X components of them together on one axis. And then on the other axis, you're adding all the Y components together. Does that make sense?
I guess.
Yeah. Now, in terms of natural forces which you'll experience, gravity is acceleration straight down. So if I set the velocity to some value and then set it to play, it'll move, the position will go up a bit and then will tend to go downwards. If I, give it a bit of a stronger jolt upwards, it'll move up, soaring high in the sky, but then it slows down and then falls back down. So this is literally a simulation of gravity. Now, it will continue to fall down, well, infinitely, so we probably want to give it a floor. And we'll also probably want to refine, like, we don't really want to have acceleration just kind of free floating everywhere. And it really depends on the context of what we're making. Since if we go back to this, what we have here, this circle here, when we click it, it runs the event A, which is like applying acceleration. So it sets v to v plus f over 10. And f is the location of this point. So it's applying this vector to the velocity when you click it. And the gravity is being applied automatically right here. Does that make sense? Now, I can share this graph right here. Yeah, and this one right here, I can call this motion vector demo 2. Copy this, paste it in the chat. So we have these two so far. And I think this leads us into the next idea. Well, I guess we can save the friction for later, since we have a term here, F, which I've set to 0.99, which is the friction of the system. But before we do that, we won't want to apply arbitrary acceleration to it at all times. And I'm wondering if we should start a new graph or kind of transform this one. I suppose what we could do, we can keep it the same and then just set acceleration to be 0 on the horizontal and then minus like 0.01 downwards. Let's move this position back up here so we can see what we're doing. So then the gravity will be much weaker. Set those back to 10. Where on earth is that point going? Trying to escape. It's like very slowly accelerating down. Let's pause that so we can bring it back to where it's supposed to be. So I suppose, yeah, right here would be a good place to bring in friction. And the easiest way to apply friction is just to multiply something by the velocity every time it updates. So if we have little f for friction set to 0.99, which is slightly less than 1. So you multiply it by 0.99 and it gets a little less than what it currently is. And if you keep on multiplying it by 0.99, it'll slowly get smaller and smaller. If it were to just be like 0.9 or 0.7, the friction would be a lot stronger. But 0.99 is like a nice amount. So we can have, a folder called friction. Just put that in there. And where we put this is right here. When the velocity updates, whatever the velocity ends up being, we multiply it by f. So if we run play, it will slowly slow down and begin to fall very, very slowly. Here, let's remove that. Remove that term. And that term, I guess. Oh, it went out the screen. Suppose we can leave the 10 there for the velocity so you can see what we're doing. And we can really just, I guess the acceleration can be like that. So if the velocity is set to some initial value, it shoots up, slows down, and then it falls back down very, very slowly but surely. And notice it has hit terminal velocity, because if friction were 1, it will keep on accelerating down, gaining speed, just always getting faster as it approaches infinity. But if it's 0.99, kind of messed it up since it reset. If I make it go really fast downwards, its downwards velocity will slow down until it hits a constant velocity. And this is terminal velocity. And just like in real life, there's only so fast you can fall down because of the air resistance. And that's basically what this is. So if you keep on multiplying it by 0.99, it hits a limit where the amount that's being added is being cut off by the friction. You see what I mean? Any questions about all this, or? How's your graph looking, Theus?
It's looking alright, I guess.
Okay. So then from here, now that we have, you got the friction in place?
Yep.
Okay. So the next thing to do is to make it not, fall through the floor. Since, we kind of want to bind it somewhere. So for that, the first thing we can do is to make it actually stop at the ground. Now, of course, we first have to check, is it below the ground? And if it is, then we should do two things. The first thing is force it back up at the ground. And then the second thing is invert the velocity on the y-axis to make it bounce. Does that make sense? Okay. So, what we're going to do, just like I had here, we test, in the tick, we test some collisions. If the y component of the position is less than 0, we run the collision event, which forces the position back to the floor, and then it inverts the velocity. So we'll implement that now. So we'll create a folder called collisions, and we'll number the collisions, because if we have a wall or say a square in the middle of our environment, each one, it kind of collides in different ways with each one. So we'll start with the floor. We'll call it capital C1, and then this will be an event much like motion, but a little bit different. So P is set to a point because the x component of P dot x is how we access the x component of it. We add to it the x component of velocity divided by 10. The y component we just set to 0. You can probably actually remove the divided by 10 now. I think it served its purpose. And so that's what happens with the position. The x coordinate is set normally, but the y position is forced onto the floor. Now the velocity, on the other hand, what we do here is, like before, the x component of the velocity adds the a component of the acceleration. No, the x component of the acceleration, a. And then the y component, what we do is minus that. So minus v dot x minus a dot x, just like here. Oh, and we'll probably want to apply a scalar to actually set that to positive. So we can also multiply by 0.5 so that when it bounces, it loses half of its energy. And then we multiply it by f. Now instead of running m, go on.
Could you please recap what you did at for the point?
Yes. So for the point, me zoom in to make the font bigger. So for the point is set to the x component is p dot x, so the x component of p plus the x component of the velocity. The y component is forced to be 0, so that it can only end up on the floor. And this is if it's below the floor, it is snapped back onto the floor.
Yep, got it.
Okay. Yeah, and velocity does the same thing basically, where the x component is unchanged, but the y component, oh, it should be y. The y component, it takes it inverts it with the minus sign, multiplies it by 0.5 to cut it in half, so that each bounce is successively less powerful than the last one. And then it adds the acceleration as usual, and then multiplies in the friction. Set the zoom back to normal. And now we have to actually trigger the event. So we'll create a new event. Let's put that with the events. We'll create a new event called T for tick. Instead of running M, we'll run T. Now T, for this we're going to want to use a piecewise function. Now piecewise is, we check a condition, and if that condition is true, then we do this. Otherwise, go to the next condition and check that. So it's kind of like an if-else sort of thing, if you're familiar with that. So we get our curly brackets to start with, and if p dot y is less than or equal to 0, then we run collision 1. Otherwise, with a comma, run M. And so this should, if I move the position up here and run the ticker, oh, it went way too fast. Here, where did it end up? It's somewhere high in the sky. And then, oh, something went wrong. It didn't bounce. Let's see why it didn't bounce. Inverted that. And that, is that what it's supposed to be? Yes, since yeah. I was kind of curious that I multiplied f by each one on the inside here when it should be on the outside. Move that out. There, that's cleaner looking. You're always going to run into weird behaviors like this when you're working on stuff. Oh, I see. I didn't apply the coefficient to the acceleration, which I believe I should have. So if I just do that, move this back over towards the center, change the velocity to be a little bit up, maybe a bit to the side as well, and run it. Oh, nope, it's still not bouncing. Maybe it's because it's bouncing too quickly. If I remove that 0.5, maybe it is actually bouncing, but it's too volatile. Oh, well now it's totally freaking out. What was different here? You see, I'm glad I set up this here, since this is a working example. So I can always look back on this one and see, why is it goofing? So yeah, if the y component is... Oh, that's right. Silly me. It's not about where it currently is, it's about where it's going to end up. If where it's going to end up is below the floor, not where it currently is. Yeah, so put that in parentheses, p plus v dot y. Okay, that's more like it. So if we, p dot v, or p plus v is this green dot here. If this dot, where it's going to end up in the next tick, is under the ground, then bounce. Ah, that's more like it. Now it's actually bouncing. So then we can add back that 0.5 and cause it to have decay in the bounce. So if we grab the position and drop it, it drops to the ground. It wasn't that sweet. And it's really heavy right now. Let's lower the gravity a bit. Make gravity half as strong. And the real key here, if I pause it for a second, move the position somewhere, set the velocity to, let me grab the velocity. This little green point here, that, if that is, like, if it's going to pass through the floor, not if it already has passed through the floor, if it's going to pass through the floor. If this little green dot here is below the ground, then it will do the bounce. Does that make sense?
Yep.
Okay. Thais, does that make sense? Devin and Henris, everyone kind of on board with this idea?
Yeah.
Yeah, it makes sense.
Okay. I gotta make sure I'm not going too fast for anyone, since my brain tends to go a million miles an hour.
Well, I can say that we went a little fast with writing the graph, and I kind of got lost a bit.
Okay.
So yeah, we might need to recap some things for me, but I guess I can watch video later.
Yeah, so what parts are you stuck on? Like, say the ticking
Like,
function, maybe, or?
I was stuck at like the implementation of acceleration. For example, when we pair acceleration with velocity.
Ah, yes. In terms of, like how this is animated, or how the functionality works, or what?
How the functionality works.
Okay. So you got the idea that acceleration is to velocity as velocity is to position, right?
Yep.
Okay. Is there any particular area where you're kind of lost with that, or is it just kind of like a general thing?
I think it's a general thing.
Well, basically, the core principle, every time it updates, every time the ticker runs, and say if you're doing this in Minecraft, it'd be every tick. You would add acceleration to velocity, and then you add velocity to position. And you just keep on doing that. You just keep on with that cycle. Oh, and of course you multiply the friction by whatever the current velocity is to make it shrink down and tend towards 0. You could also do that with acceleration, but in most cases that would just make it kind of goofy. And so what does your graph look like right now? Like, if you were to set it up like this, hit play, does it bounce like that on your graph?
Definitely not. I didn't implement it yet because I
Okay.
was trying to pay attention to the explanations you were giving for the
Yeah.
bounce.
Yeah, so I'll save the current state of the graph and paste it in here. Yes, I will, in a future lesson, I'll show how to apply these principles to various languages, including MC function. Yeah, so that'll be really cool. And it's interesting with Minecraft commands, since you don't really have the tools that like Desmos has. You kind of have to do everything manually with scoreboards. So you got your velocity scoreboard. You add your gravity constant to it to make it move down, and you add that to the position. But then you got to write the position to the entity using execute store, entity and all that. And Minecraft's kind of janky with that.
Kind of like creating our own motion system, if I'm correct.
Yeah, exactly. Okay, Henris, how is yours acting right now, then? Okay, Okay, which new bit did you add? Is it with the ticker function that you didn't add? Are you running the right function? Okay, let's see here. Okay, so we got the acceleration defined, we got the thing drawn out. Okay, the ticker function's there. Okay, so the ticker function's proper. Okay, so what is the ticker function actually running? Or the ticker at the top. Is it running M or is it running T? Okay, it's supposed to be running T. Since we've kind of moved it back one layer, we're running this every frame instead of this every frame. That way we can have more control over it. If the object is well above the ground, it runs M, just for regular motion. But if it's gonna go through the ground, then we run C1. Okay, that's good. Okay, and is everyone else caught up with all this and how it works and how to use it?
Yeah.
Okay. You're absolutely sure, though? Since I don't want to...
I think it's best if you if you do a brief recap of everything.
Okay, yeah. So, got 3 parameters here. Acceleration, velocity, position. Acceleration tells you how velocity changes. Velocity tells you how position changes. In computation, you do that by adding acceleration into velocity, and then you add velocity into position. And this causes it to evolve in really cool and dynamic ways. Acceleration, you just set to straight down, to be like gravity. And we can add other forces as well, like in this graph where you hit this button and it applies an acceleration in some direction based on where this vector is, because I can shoot it that way, I can shoot it that way, and bring the little cube back into view. And we also got friction here. And the friction prevents it from accelerating off to infinity. It slows it down. And this, you multiply it into the velocity every tick so that it slowly tends back down towards 0. That way there's an actual terminal velocity. And then there's the collision system, where in this tick function we check if it's in somewhere that's not supposed to be, run the collision function here, or the collision event. Otherwise, make it move freely with M. And so that's what we got so far.
I see.
Okay. Now the next thing we could do is make this wall have collision. And so basically we do the exact same thing, but with the x-axis. So if we interject it right here, right after C1, comma, and then P plus V dot x for the x component. If it is less than or equal to 0, then run C2. Now C2 doesn't exist yet. If we hit this gear, and this little prompt opens up, we can click this to duplicate this expression. We just hit done. We can change that for C2, and we can go in here and switch everything out for the other axis. Kind of shuffle everything around, make it 0, and then PY
So we swap the axis around.
Yes, we switch the thing around.
Make the extra. Yeah.
Yeah, so we can cut and paste this and move it to the end. Replace x with y and y with x. And yeah, it's that simple to make it do that. So if we pause it for a moment, set the velocity to why is the velocity stuck? Oh. Okay, so if we set the velocity to say this direction, let's make it pretty strong velocity, and we play it. Oh, it was sliding on the ground when that happened. Oh, I hit the acceleration instead. Oops. Let's reset the acceleration back to where it's supposed to be. In fact, we can probably just hide the acceleration now since it seems to be getting in the way. So bring the position back down. It went into outer space. So we bring this back down. We move the velocity to, like, say, right there. Let's make the gravity a little weaker while we're at it. So it bounced on the wall, and now it's going to fall down. If we set that to 3, it'll be a little stronger. Let's bring it back down at a adequate velocity. Now it's slowly falling down back to Earth. Apply a little force to it, and it bounces on the wall, and it falls back down. Maybe the gravity needs to be a little stronger again. This is really satisfying to watch.
Can you please scroll down to the C2?
Yes,
line?
right here.
Thank you.
Yeah, and in actual code, we could, once it like hits the ground, we could add like a little effect where it makes like a little poof or something.
There's a guy who did that to his girlfriend, and he pooped his pants. Like, he pooped his pants.
I think by lesson 4,
On the internet.
we'll have enough established so that I can show how to create a game in with HTML, JavaScript, and WebGL all kind of in one package. So that'd be really cool.
Or you can give it to the ball.
Now, one issue this has is that it is not capable of colliding with 2 walls at the same time, since it does one check and then the collision function, and if that fails, then it does the other check. So that means that if it's sliding along the floor, then it will just ignore this wall entirely. But it's technically possible to fix that here. It'd be a little tricky, but it'd be a lot easier to fix in actual code and not Desmos. For Desmos, all we need is to demonstrate the like how the math works, basically. How's everyone's graphs looking?
Looking good.
Is it bouncing on the walls and the floor and everything?
Yes, it is.
Nice. You know
I'm
what?
trying
Go
to
on.
add C2 to the if statement.
Yes. So in T, let me zoom in. So this is the first condition here, and then we got the comma to separate it. The second condition is almost exactly like it, except we're testing the x-axis instead, and then we're running C2, and then you got your comma, and then M.
Oh, I see. So, okay. Thank you.
Okay, yeah. That works. Look how blurry it is. Yeah, and something that's kind of annoying is up here, when the velocity gets so slow that it turns into the scientific notation, you can't drag it around as a point, which is kind of tedious. Have the point get way up there. So I believe the next thing to do is to create the clickable thing like we have here to make it more convenient to play around with. Is everyone caught up with how the graph exists right now?
Yeah.
Okay. Okay, so Henry has his. Yeah, it looks like it. Now, here's the thing about implementing stuff with code and everything. We're not going to be doing tests, really. The criterion is, does it function? Does it work? That's what we're really looking for. And so, if what you're creating functions, then we got it. So there's not going to be like a written test or anything. It's just, does it work? Does it feel nice to use? And so on. Devin, how does your graph look?
I didn't, I wasn't building along, I was just watching.
Oh, okay, yeah, that's fine. You don't have to. You can, look at all the examples and everything. Just might be a little harder to follow along if you're not, building it with us.
If I do two things at once, I get lost.
Yeah, I can understand that. I'll make sure I slow down the pace for future lessons, especially as we get into more complex ideas.
Yeah, thanks.
Yeah. So now, what we should do is create this little thing, a force that we just apply to it. So, we can create a new folder, call it force, have capital F, save little f for friction, capital F for force. Let's make this purple. And we can label it force. We can also hide velocity now. Hide acceleration while we're at it. You can turn off a whole folder, which is nice. Now force, what we're going to do here is we want to draw a circle around it that we can click as an object, like this thing here. And so we remember what we did earlier with the Pythagorean theorem with the circle?
Yep, x squared plus y squared equals 1 squared, or
Yeah.
z squared.
Yes, precisely. And so that's how we draw our circle. Now, we want the center of the circle to be where force is. So what we'll do is we'll parenthesis off both x and y, and we will subtract the location of F on each axis. And then voila, it's centered. And so what we're really doing is we are treating where force is as the origin, in order to draw the circle. So if we do, obviously force minus itself is 0, so where it is will be treated as the origin when we square it and add it to the other square. And technically we could square root this and put all of this in there and then remove the square term for that, and it's the same thing. But since we're dealing with a constant term, no need to square root, since square root is unnecessarily expensive for this purpose. And what we'll want to do here is get a force going, a special event which will run when we click this. So this event, let's see what we should call it. What do you think we should call it? Applying a force. We could call it like capital A for apply, or that's kind of weird. Maybe F1. Like capital F1 for force to apply it. And basically what we're doing is V event. Yeah, so we're setting V to be equal to whatever the velocity currently is plus F divided by 10. And what we do now is you hold down the little button for the circle. You set it to be clickable right here. And then on click F1. Which means that now, if we click it, it applies a force to our little object. Oh, it's still, it doesn't like to interact with that corner properly. But yeah. It looks like we should switch around the events since it's more likely to slide along the floor. So if we go back up here to tick, we select the first event right here, Control X to cut it, and then we move it right here afterwards. Boom. Now that we've switched them around, it will be more stable next to that wall. We can probably also shrink that obnoxiously large circle. Set it to 2 instead of 10. And it seems to be working quite well. Maybe weaken the gravity a little bit while we're at it. Go up to acceleration, so to say, how about half of what it currently is? Ah, that looks nicer.
May you please tell us how can we add an event?
Oh, you mean for the clickable object, or?
Yeah.
So what you do, so you got your thing here for the clickable, and it doesn't have to be a circle. It could literally be anything. It could be a polygon,
yeah,
anything. So you hold down the button to bring up this prompt. There's a clickable toggle on the bottom, and you hit that, and then on click, the event which we have assigned to apply the force to the object. Does that make sense?
Oh, I see.
Yeah.
Yep.
Yeah, because if we run this event, it does exactly what it does to click this. And we can move this anywhere and apply forces in any direction that we want. You even spam click it to give it a lot of force all at once. Just so funny watching this thing bounce around all chaotic like.
So acceleration becomes F on click.
Yeah, pretty much.
That's how we
Yeah, and
that's how we apply the force. Okay.
yes, and force is, it's interesting because force is kind of like a change in acceleration, but it's a momentary thing that you're applying. Unlike gravity, which is a continuous thing. I mean, it's a momentary thing in the simulation, but in the real world, force is applied over a period of time, and force over time, I think, is referred to as work.
Work is force over distance.
Force over distance?
If I'm correct. Or force, yeah, force over. I think force over time is power or impulse.
Yeah, I'll have to go back over all the terminology and stuff.
Yeah,
I just
me
know what
either.
I know what it does in the math. I don't know what people call it. Plus, what people call it kind of is regional as well. So long as you understand what it's doing and you can simulate it in the code, then that's what really matters. Being able to communicate those ideas with other people, like I'm doing now, is very important as well. So that's a reason to know that. Here, let's see. Definition of work in physics. When a force acts upon an object while it is moving, work is said to have been done upon that object. Work can be... Okay, is the energy transferred to or from an object by the application of force. In simplest form, it's often represented as the product of force and displacement. So yes, force times distance. That's work. Okay, so it's not quite the same idea as what I was talking about.
That might be impulse, if I'm correct. From what I remember from my mechanical classes.
Yeah.
From mechanical classes, yeah.
Yeah, that'd be good to look into all that. So, how is your graph looking? Is it behaving properly and everything?
I see arrows over at the tick function. I mean, I'm trying to implement C2 over the if statement, but it doesn't seem to work, even if I typed it incorrectly.
Let's see what you got as your tick function right now.
Hang on, I'm gonna show. Sick.
And Henris, if you could show me what your force event looks like and what the force object looks like. Like this being the force object and the clickable and everything. Okay, let's see what you got here. Okay, so the event... Oh, aha, you see, on your clickable object, you're running T when you should be running F1. So it's literally just repeating the normal tick when you click it. See, it should be running F1. That way it actually applies a force to it instead of just making it tick like it normally would. Yeah, and trust me, there will be a lot of debugging when we get into the more complex subjects. Since as time goes on, we're going to explore physics in 3D space, rendering three-dimensional space, with like ray tracing and ray marching and all sorts of algorithms like that. The more complex they get, the weirder the bugs can get. And so I think I'll have a special lesson dedicated to how to properly debug something. Since, knowing how to find the issue is crucial.
Okay. So I was just trying to screenshot my browser, and some weird dots just replaced some expressions.
That's weird.
That might be a Desmos bug, I believe. Am I trying to... I think I got it.
Okay.
Just a sec. Look.
Wow, what is that?
I don't even know. I just pressed like Alt and then the letter U because I have a keyboard without a numpad on it. And I have to use FM.
Yeah, I think an issue I see right away is that you're using acceleration and the force kind of interchangeably when they're slightly different. So we're using acceleration to represent gravity, which needs to be kept separate from the actual force.
Hang on.
What does Alt U do?
I refreshed my page and now I need to...
Oh, if you refresh the page, it'll probably
and
wipe the changes to the graph. Here I can send the current state of the graph. And so what you had here, you know, you're using acceleration where the force is supposed to be. Normally acceleration, let me make it visible again, is supposed to be extremely tiny, pointing straight down. Otherwise, it just becomes way too volatile.
Oh, yeah, I may have set it to 0, if I remember correctly. That might be the case, I don't know actually.
Yeah, it being set to 0 would make it be 0 gravity. So if I set that to 0 and then hit the force, you'll notice that...
Yeah, it's just going to float.
Yeah, now it's floating in outer space. So let's set that back to minus 0.025, not 3525. Now we can, you know, move it around normally. Seem kind of quiet, Theus. Are you following along?
Yeah, I am. So I just had my microphone muted for a little bit.
Okay. So funny watching this move around.
Yeah, it's fun to
I
mess
agree.
around with.
Yeah, and you know, we can make it look like this one and turn it into a little green square with the polygon expression, but it's not really necessary. You know, it just being a little point works just fine as well. And so with the force thing that you were doing earlier, the force has to be a separate thing, as a separate point right here. Capital F equals some point in space that you drag around. And you know, you have a special event associated with it. So when you apply force, you just modify the velocity directly. Since the acceleration, it represents the static acceleration, the continuous one, versus the force is like a single decisive event. And in a sense, how we're doing the collisions right here could be done as an application of force as well. When you look at Newton's law of motion, one of them, you know, for every action there's an equal and opposite reaction. So when two objects interact, whatever force it exerts, whatever force object A exerts on object B, that same force is exerted back on object A, but in reverse. So you'd multiply its force vector by -1 to point it back, and then that is applied back to object 1, and it gets shot back. And that's how bouncing occurs, basically.
So basically, you have two objects going straight for each other.
Yep.
The object with the force 1 gives a jolt to object 2 in the direction of its force, and so does the other object as a reaction.
Yeah, and so there's...
According to principle 1, I believe. Forgotten.
Yeah, he has 3 of them, and I forget the ordering of them. They're Newton's 3 laws of physics. Okay, first one, objects in motion tend to stay in motion. Okay, so the first one is inertia, and then the second one is force equals mass times acceleration, and the third one was what we were talking about. For every action, there's an equal and opposite reaction. And all 3 of those are useful here. But the force equals mass times acceleration will be more useful later on when we get to more complex simulations. Because right now, this is a very simple simulation. Now, something I think we should do as we're coming to a close, maybe not just have a floor and a wall, but also a ceiling and another wall. So like we trap the little dot in a box. So what we can do is kind of animate our box first with a polygon. So a polygon is a function, and it contains a list of points. These points will be the vertices of it. So we can have one at 0, 0. Let's make it 20 by 20. So we could have 20, 0, 20, 20, and then 0, 20. And we got our little box. Let's set the wall to black. Let's remove the fill. Boom. Got a box. I think there's a way to change the width of the lines. Yes, so if we set the line width to 5, make it extra thick. So now, what we can do, because obviously it's just a visual, so it'll pass right through the wall. So, we will create 2 new collision functions, C3 and C4. One will be a duplicate of C2, and the other will be a duplicate of C1. That way, we're interacting with the walls properly. So we'll set that to C3, set that to C4. Now C3 is interacting with the ceiling. Really, the only thing that has to change is instead of setting it to 0, we set it to 20. And the same thing with C4. Instead of setting it to 0, we set it to 20, because that's how big the box is. You following?
Yep.
Okay, so then what we do, we go over to the tick event. We copy the one for the, what is that, the wall? That's the wall collision detection, I think. No, C2 is, yeah, C2 is for the wall. So we copy this one. We make it run C4 instead. And instead of equal to or less than 0, we do is greater than or is equal to 20. And now, what is it doing? I recall seeing it kind of go through the floor earlier. Okay, so yeah, that's functioning. Okay, so then we do the same thing, copying this last event here, C1. We copy paste it. We run C3, and we do the same thing with the condition check. If it is greater or equal to 20, then it will run collision 3. And if none of those collisions succeed, run motion. And we zoom back out. And now, if we set the force to something really, really high, now our little dot is bouncing around the box like a maniac. You can spam click this and just bouncing all over the place. And these expressions can get kind of long. I've had expressions that went well beyond the width of these things. We won't run into those for a while.
That goes bouncy, bouncy.
We could also make it a little more volatile by changing this 0.5 term to something bigger. So if we define a new parameter, let's call it absorption. So how about capital A for absorption? Right now it's 0.5. What if we set it to, say, 0.8? So then we just replace all instances of 0.5 with A. And then, yeah, the motion lasts longer. Although if you want something really freaky, making this something bigger than 1 makes that with each bounce, energy is added. And so we got a perpetual motion machine. Oh, went wrong, oh boy. Set that back to 0.8. Ah, there, we're back. But yeah, probably don't want a perpetual motion machine. It's funny how easy it is to make something physically impossible in a computer.
Yes, sir.
I agree.
Yeah, and so think of the possibilities with just this alone. Imagine that's a ping pong ball, and this force vector is applied when we swing the paddle at the ping pong ball, and so we apply a force to it, and now it's bouncing all over the room. It's bouncing on the table. You can easily make a ping pong ball game with this. It's like arcade pong, but better because it actually has gravity.
Yeah, we were doing that in Scratch, I think, in year 7. I'm not a big fan of Scratch. I mean, it's cool, but it's a bit boring, really. But we essentially made like a replica of Pong, right? And all these kids searched online and stole code from this website to give it like gravity. The only issue was that the game actually stopped working to give it gravity, So like they were like, oh yeah, look how cool this is, this is awesome. But the game didn't actually work anymore, So...
Yeah, and that's why it's like with principles like these, the math behind it is so simple. You just add acceleration to velocity, add velocity to position, and boom, it starts moving around, all physically realistic. And all that. And if you know that principle, then you just make it, because this in code is really simple, ridiculously simple. And so you don't have to go and steal code from someone. You think about what's happening and you write the code to do that. And and something, it kind of bothers me a little bit when I'm watching YouTube videos made by like Game Maker's Toolkit. He does a lot of this stuff, and it kind of irritates me on the inside when I see him using libraries for basic physics, like applying gravity to something. And it's like, it's such a simple thing. You could, just a couple lines of code, you could implement it.
Yeah.
But that just...
I myself I am quite surprised to see how easily we can implement gravity or bounciness.
Yeah.
Like
Just add velocity to position and acceleration to velocity.
Yeah.
Yep.
I still don't really understand algebra though, which I guess is an issue.
Yeah.
I mean, I get that you like assign number to a letter and you can like play around with that, but
yeah, and that's what we're really doing with this, because like we're setting f to be equal to 0.99, but if we didn't know what f was and we saw the little ball behaving in some way, then we would be able to calculate what is f.
oh wow.
Yeah, so like if I were to open up a new Desmos tab to get a blank slate, if we have some value a, we don't know what a is. Let me expand that so that's kind of hidden, because that kind of exposes the answer. So if we have some equation, let's say 3a minus 4 equals I don't know, minus 2a. So a is clearly something satisfies this, but what is it? So what you do here, when you got an equation, the rule is simple. Whatever you do to one side, you do to the other side to make sure it's equal. So if we add 4 to both sides, then we do this, plus 4 and then plus 4. Well, minus 4 plus 4 is clearly 0, so that cancels out. And we got this. So then we can add 2a to both sides. So if we add 2a to both sides, we get this. Well, that's clearly 0.
You can think of it as just moving something on the other side of the equal sign and then changing its sign. It's much easier for me, at least.
Yeah, and then when you got something like this, what you do is you isolate the a. So if you wrap that in parentheses, both these are multiplied by a. So you can remove the a from the inside and bring it out, since it's doing the same thing. Mind you, 3a is just 3 times a. So it's the equivalent of a plus a plus a. And so if you have, 3a plus 2a, that's a plus a plus a plus a plus a. And that's clearly 5 of them. So this just becomes 5a.
I see.
Yeah, now we got 5a equals 4. So now if we divide both sides by 5, then, you know, that divided by 5 and that divided by 5. Well, 5 divided by 5 is clearly 1, so that cancels out. And voila, a equals 4/5. Which means if you plug 4/5 into a, into those two, then it will be satisfied. And yeah, that's kind of at the root of what algebra is. It'll take a lot of practice to get the hang of it, and, you know, experience with these things. You know, you just gotta solve problems, basically.
I see.
Yeah. So keep that in
Well,
mind.
to be honest, my maths knowledge is possibly, well, it's basically extremely basic. Basically.
Yeah, and not all facets of computer science require math. It's just a lot easier if you know math. And
I guess so.
yeah, and since now you see how to do a basic physics simulation like this, you know, you take whatever acceleration is, you add it to velocity, take whatever velocity is, add it to position, but, you know, apply a friction coefficient to it first. By the way, a coefficient, if you have some number, a coefficient is the thing that you multiply it with.
Alright.
That'll come in handy later. And what's really fascinating is that this idea here, simple little idea, is at its core a numeric simulation of a differential equation. Now, that might sound kind of complicated, which it is, and that's in like a really high level of math. But the fact that we got such a high level of math, like the concept of it in such a simple little thing, shows that even the most complex of math kind of loops back around on itself, and it has like a simple heart, you know what I'm saying? And, you know, eventually we'll see stuff like this with
Oh, wow.
pendulums and stuff. You know, more sophisticated physics simulations. I actually used this to make a rope in Minecraft to use swing on for a map.
Oh. That's awesome.
Yeah, and, you know, this thing we created has 27 expressions. You know, you see the little number on the corner here. 27.
Yeah.
This thing has 119. And there's
Jesus.
big matrix solutions and, you know, solving parameters and blah, 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 blah. So this is like high-end math. So we'll get to stuff like this eventually.
I think it's going to be a long time before I get to stuff like that.
Yeah. We'll see. We'll see, you know, when everything comes along. Let me close that. Oh, we'll also get into 3D projection of space.
Wow.
Yeah, let's see. Let me grab my generic perspective graph. This stuff is possible in Desmos 3D. And mind you, we won't be only using Desmos. We're also going to be using ShaderToy. We're going to be using Python. We're going to be using HTML and JavaScript and Minecraft functions. We're going to be using anything we want. Just depends on what the topic is for the day. And so, it is now 2:34. That concludes the first weekly lesson of Nerd Academy. I will send the link to the latest graph here. And what I'm thinking for now is experiment around with like the parameters of this thing. Maybe like change the size of the box. Maybe generalize the collisions so that you don't have to have 4 of these. Maybe if you only had 2, maybe even 1. And there are more complex things you could be colliding with. Like, for instance, if there were like a triangle in the middle of that square, and if it were to hit like a slanted side, the way it would bounce would be different. And so you'd have to kind of deal with that. And that deals with some more complex vector math, and we can probably have a future lesson about that. But for now, I'm thinking play around with it, you know, mess with the parameters, get the hang of what it's doing.
Alright.
Yeah. And so, I think with that, that concludes the lesson, and I'll see you all next week.